Please welcome to the stage, founder of Black Hat, Jeff Moss.
I'm really impressed by the smoke machine. That's super cool. You know, we bring in all of this stuff. It doesn't exist. It's built just for you. Hey, so thank you for coming to the second keynote, day 2. So today I'm going to do some housekeeping announcements before we introduce our keynote speaker, Moxie. Yesterday it was a pretty tight schedule, so we just put it off until today. So for those of you who are not familiar with Black Hat, or maybe this is one of your first time, let's just see a show of hands. Who here is this your first Black Hat? That explains why you're here. Awesome. Welcome. So what we try to do with Black Hat, one of the things, is we try to involve different communities that might be just getting their start, right? We're a pretty professional, big-name event, and it might be intimidating for some people to get here. It might be hard for them financially. And so we have the scholarship program concept where you write papers on a topic, security topic, they get sent in, they get reviewed, and then a certain number of them are accepted, and you get to come to Black Hat. So this year, we had a total of 308 accepted scholarships from students, women's groups, veterans groups. We really try to cast the net wide. So just curious, if anybody in the audience that is here on one of those 308 scholarships, I see some down here, over here. Right on. Thanks, guys. So one of the secrets to Black Hat, or any conference in general, is making friends. And so don't be afraid of asking questions or approaching people. The thing with information security is we absolutely know for a fact that nobody knows it all. Like, there's just too much going on. There's too much specialization. And so if you ask a question that you think is dumb, somebody else might think that's totally smart because they're not in your field, they're not in your specialization. So just ask questions, right? So our briefing sessions will start, like yesterday, at 10:20 after the keynote ends. The business hall will be open, level 1, in Bayside A, B, C, and D. And something that's also new for this year, yesterday was the first day, we have additional main stage presentations at Oceanside A on level 2. And so we'll have 2 big-name speakers. We have Director Jennifer Easterly from CISA giving a presentation, followed by Director Harry Coker, Director of the Office of the National Cyber Director. And that's this afternoon at 12:15. So it'll be those 2 presentations back to back. You should check it out. And finally, we have, at the end of the day today, we have what we call our lock note. We kick it off with the keynote. We end the whole conference with a lock note. And there what we're doing is we get the Black Hat Review Board team members, some of them that aren't afraid of speaking in public, and then we get them out, and I ask them questions, and we see what do people think. What was good with the show? What topics were new this year? What trends changed? Like, everything used to be about threat hunting and what was it? Deception networks. We didn't see anything on deception networks. Why is that? And the idea there is that we want you to feel like you're watching a group of friends and experts have a conversation. And then about 2/3 of the way through, you can start asking questions and see what their opinion is on whatever you have in your mind. So it's a nice way to kind of wind down the conference. Now, for our keynote, before I introduce Moxie, who I am super excited is here. It is really incredible. I'm kind of a fanboy of Moxie's. I was early user of Red Phone, which ultimately became Signal. And it reminds me a little bit about how people in security, sometimes we get ahead of ourselves, right? We're so obsessed on the technology, we'll do something, and we're ready for it, but the public or businesses are not ready for it yet. And what comes to mind is Marcus Raynham, who's famously said, "I've made 3 people millionaires, and I'm not one of them," for things he would invent and sell off, right? One of the first commercial firewalls, didn't work out for him financially, but hey, he moved the needle on. So he had this thing called Network Flight Recorder, NFR. And the whole idea was like it was a black box that would go on your network. And then if anything went wrong, you could go to your network flight recorder and you could figure out what happened. Brilliant. He was 10 years too soon. They pivoted and pivoted and pivoted. It turned into like IDS or whatever. 10 years later, NetWitness comes along, just destroys the market. And you're like, it took 10 years for that idea to be ready. And so I'm really curious how an idea that Moxie had for just a secure messenger, it was sort of in the right time. By the time the product was mature, by the time the products were ready, the consumers were ready, businesses were ready, right? Hackers who've been fantasizing about secure messaging since I knew what it was, but it was never really ready until Signal came along. And so I'm really excited to listen to his insights. And so it's my honor to introduce Moxie Marlinspike. Thanks.
Yeah. Hello. So I'm going to talk with Jeff in a moment. We're going to have a fireside chat. Presumably the fire will be laser generated or something like that. But I wanted to give you all a pitch first. The pitch is that when I was a kid, magic existed. I didn't get around to reading the Harry Potter series until I was an adult. And I'm glad I read it. Like, it's good, and a lot of cultural references suddenly made sense to me. But the one thing that I didn't really understand was their depiction of school, and more specifically, school work. It seems strange to me that they didn't want to do it. I mean, don't get me wrong, I hated school. I come from the American Muggle school system, where I like to play the road trip game, is it a school or is it a prison? Is it a prison or is it a school? Is it a school or is it a prison? My middle school had a required music class where they're going to introduce young people to this amazing, sacred thing, music. And the class was handbells. I don't know if you know how handbells work, but you get a bell, you're like a note, you're just like C sharp. And then you wait in the music until it's time for your note, and then you ring the bell. If you were to assemble the world's top minds and ask them to spend a year designing a curriculum with the goal of destroying any child's natural desire or curiosity to learn about music, I don't think you could do better than this. So, which is all to say, I get it. School sucks, drop out if you can. But their school did not look like a prison. And more specifically, there they are in a library, surrounded by books that contain magic spells. And if you learn the spells, you can do actual magic. You can fly, you can breathe underwater, you can travel great distances at great speeds. And yet there they are in the library complaining about having to be there. If I had access to that room, I don't know that I would ever want to leave. But consider for a moment that maybe this is already the world that we live in today. We too have rooms filled with books, and those books contain knowledge. And if we learn the contents of those books, we too can do amazing, magical things. We can fly, we can breathe underwater, we can travel great distances at great speeds. And the knowledge for how to do all of those things is contained within the books around us. All we have to do is learn that knowledge, and we too can do amazing magical things in our world. But it doesn't exactly feel the same, right? There's something that feels different about our world and the Harry Potter world. To me, the big difference is that in the Harry Potter world, all they need is knowledge of the spells and a wand. They don't need to assemble and motivate large groups of people. They don't need permits. They don't need to figure out how their magic fits into a larger economy. They don't have to allocate large sums of capital in order to cast their spells. In our world, if we try to cast this spell, we're going to need more than a wand. And that is what makes us muggles. Not that magic doesn't exist in our world, but that the execution of that magic does not feel as magical. Okay. Speaking of magic, but software is different. When I was a kid and discovered software, magic existed. To make amazing things with software, you do not need to motivate and assemble large groups of people. You don't need a permit or a license. You don't need to allocate large sums of capital. I don't know if this is proving my point or not. The only thing that you need is a computer, and it doesn't even have to be a good one. And that, I think, is an exceptionally rare thing in our world. It is actual magic of the Harry Potter variety. But I feel like this magic has been somewhat diminishing over time. So I want to talk about that a little bit. Software, to me, is a really interesting, unusual thing. People who work in software usually call themselves software engineers, and yet if they went to university and graduated with a degree, it is in computer science. That is immediately kind of a weird thing, because science and engineering are two pretty different disciplines. But I think that this tension about, like, what is software, how does it work, what are we doing here, is related to what makes it incredible and magical. At first glance, software seems like it's straightforwardly engineering. It exists within a fully known universe, this thing, the computer that we created and invented and know all the rules of. We don't have to discover any of them. And that is unlike more straightforwardly scientific disciplines that exist within worlds and universes that we did not invent and so do not fully understand. We have to discover how they work, and so you could say science is basically, in large part, the process of discovery. Software seems much more straightforward. It's just about getting from A to B, right? Like, we know where we are, we know where we want to be. We have to do some engineering to get from A to B. There's going to be maybe some challenges that we didn't anticipate along the way, but it's not scientific discovery. And that's unlike more straightforwardly scientific disciplines where you are not trying to get from A to B because you don't ever even know where you are or how things really work, much less where you want to go or how to get there. You're just sort of like casting around in the dark, trying to discover the rules of these worlds and universes. So software seems like it's this much more straightforward thing, where you have some vision of what it is that you want, and software development is the process of compiling and assembling the resources from the vast, complex system of computing in order to manifest that vision. But I actually don't think that that's the full story. I think that this relationship between vision and engineering is actually intertwined and bidirectional rather than linear, and that the whole of software development is filled with discovery, even though it exists within a completely known universe. Consider this computer graphics animation from the period of time when I was first getting interested in software. Here we are in the 8-bit era, and yet we have this beautiful scene, or this animation from the same era. The interesting thing to me about these animations is that they're not actually animating, at least not in the conventional sense or the values of all the pixels on the screen are calculated and rendered for every pixel 30 times a second. I mean, it looks like that's what's happening here. It's like super dynamic, we have all this motion, but that would not have been feasible given the hardware constraints at the time. Instead, these are actually images that are making use of a technique known as color cycling. Color cycling was exploiting the fact that graphic systems at the time, like VGA, were indexed color systems. Indexed color systems were developed as a memory optimization technique. The problem being that if you represent every pixel on the screen with a full 3-byte RGB value, even at a modest 640 by 40 resolution, that's some 300,000 odd pixels. At 3 bytes per pixel, that's about a megabyte a frame. At 60 frames a second, that's 52 megabytes a second. And so indexed color systems were developed as a memory optimization technique to allow you to represent every pixel with a single 1-byte color value. So you had a single 1-byte color value, and then separately, for an image, you would define a color palette. And that color palette would map the 1-byte color value to the full 3-byte RGB value. And then when every pixel on the screen was rendered, it would be, for every pixel, you would look up the color value in the index, get the full RGB value, and then the correct color would be displayed on the screen. An interesting side effect of this is that for any individual, steady, ta-da. For any individual mapping in the color palette, you have a value that multiple pixels might reference simultaneously. And if you update just that one mapping in the palette, you update multiple pixels at the same time. So with one write, you update, you can affect several pixels at a time. So you start to get some intuition of what might be possible here. People who understood how these systems worked realized that you could carefully construct an image such that you carefully chose the color values and the palette, and then intentionally cycled the values of the palette at a specific rate to construct what looked like a really compelling animation that should have been impossible. Bro. I'll use this opportunity to drink some water. Okay. Tricks like these were combined with others to create the original Amiga Boeing ball demo. In this demo, the rotation of the sphere, I think, is actually color cycling. That the sphere isn't actually rotating, but by cycling the color palette, you can create the appearance of rotation. These, to me, were non-obvious results. Index color systems were not created for this purpose, but people who understood how they worked were able to use them to create something unexpectedly great. Should go back to the 8-bit era. It's more reliable. It is, to me, an unexpected result in a long history of unexpected results. Who would have thought at the beginning of all of this that just by cycling electricity on and off really quickly, we would get all of this? I don't think I would not have anticipated that at all. That in fact, the history of software and computing has been a long history of discovery, repeated discovery, even within this fully known universe. It's a kind of discovery where engineering is actually at the basis for discovery, which makes software, I think, really unique. I'm using this example of color cycling because it's so old as to be almost uncontroversial, but it is a pattern that I've seen again and again throughout the course of my career and involvement in software, where there's this relationship between vision and engineering that is often intertwined and bidirectional rather than linear. The vision for these images, these animations, did not emerge first. Someone didn't say, oh, this is the animation that I want. That vision was developed and informed in a bidirectional relationship from an understanding of the system. Again and again, we see that deep understanding of tools and technology are what yields some new vision, some surprising result, some new insight, or solution of some kind, big or small. Ta-da! That's not always some new product or demo. Oftentimes, it's just a smaller advancement within a smaller project that maybe only a smaller group of people might ever take note of. But it almost always starts with the understanding part. That in some ways, you could say new technology is often just the unpredictable results from the combination of existing technologies that yield some new advance. And that we have created this thing, the computer, that's complex enough that we have been able to discover new possibilities over and over again by combining what it is that we have there in ways that generate new and surprising results. But it almost always starts with the understanding part. And I feel like understanding has been somewhat diminishing in software over time. Software has the benefit of relying on abstraction layers, which are incredibly useful. If every time you went to write data to disk, you had to implement all of the logic associated with storing data to disk from scratch, it would be extremely arduous. So it is, of course, greatly valuable to abstract that logic out into a reusable interface like a relational database or a key value store so that you don't have to do that. And the same is true for any abstraction layer, an HTTP library, a sockets interface, a C compiler, a game engine, or any other abstraction. But there are two ways to think about abstraction layers. One is that you can use them as shorthand for what it is that they're doing, and the other is to use them as a black box. When you use an interface as short, do you think this happens like every 30 seconds, 60 seconds? When you use an interface as shorthand, it's a shorthand for what it is that it's doing. So you use a storage layer as shorthand for an understanding of what it is doing on your behalf and how it works. Or you can use an interface as a black box where you interact with some interface and you have no idea what it is doing. The problem in computing with using abstractions as black boxes is that these interfaces are never perfectly clean. Computing is so complex that they probably never will be. And so when you use them as black boxes without really understanding what they're doing, it can sometimes have negative results, and those negative results usually compound with the size or scale or complexity of an application. And I think most people who work in software understand this. But I think there's something more going on here, which is, again, related to this intertwined relationship between vision and engineering. That if you use every abstraction, or if you see every abstraction just as a black box, that makes it actually difficult to have any vision at all. Sometimes we create abstraction layers with the explicit purpose of allowing people to interact with them and interface with them without having to understand what's going on beneath them. And usually we call those platforms. The expectation is that when we create something like that, we should actually see an explosion of creativity, because now people can focus solely on the creative aspects of what to build instead of having to think through the technical aspects of how to build it. And this seems obviously true for domains. Wait for it. Outside of computing. We might say that a filmmaker can make a film without having to understand how a camera works. And that there's probably not much of a predictable relationship between a filmmaker's understanding of the internals of a camera and the quality or creativity of the resulting film. And so we might be tempted to extrapolate from that into the realm of computing and say, well, we should be able to develop a game engine and allow people to build games on top of a game engine without having to understand how the game engine works, in the same way that a filmmaker doesn't really have to understand how a camera works. And then, in fact, when we do that, we should expect to see this explosion of creativity, because now people can focus only on the creative aspects of the game that they want to build instead of the technical aspects of how to build it. And I think the problem with this metaphor is that a camera is not actually an abstraction layer for a film in the same way that a game engine is an abstraction layer for a game. That you don't just layer a story on top of a camera. There's a lot of other really complicated stuff that's going on that a filmmaker really does have to understand in order to understand how to bring a story to light to make a compelling film. You can't just have a good story. A filmmaker has to understand all of the mechanics of how to make a film in order to make that really compelling. And that when we take this metaphor into the realm of computing and create these abstractions that allow people to interact with them without having to understand how they work, that I think we do actually see an increase in stuff. We see more things as a result, but I think it's also often a lot more kind of mediocre stuff or schlock. If we look at just a graph of game releases over time, certainly as we made it easier for people to develop games with the introduction of things like game engines that people can build on top of without having to build their own game engine, I think we are seeing a lot more games over time. But if we also graph on top of that a scatter plot of critically acclaimed games as defined by a Metacritic threshold, that is not increasing over time, and if anything might be decreasing. So I think we're seeing a lot more stuff, but we're not necessarily seeing a lot more excellent stuff. And I think that this may be connected to this ongoing relationship between vision and engineering, engineering and discovery. That in complex ecosystems like computing, there just seems to be some kind of ongoing relationship between a deep understanding of the tools that we use and the quality or creativity of the output that we get as a result. I feel like in computing, in a lot of ways, we can only truly create when we truly understand what it is that we have to create with. And maybe that's not so controversial. Like, I'm just saying the better we understand shit, the cooler stuff we can make with that shit. But I think that this applies in all kinds of meta ways to the software industry as a whole. I think, for instance, it also applies to the way that groups of people work together. In many ways, what I'm saying here is like what it takes to be a good engineer, but I think what it takes to be a good engineer is also what makes a good engineering organization. Over the past 20 years, engineering organizations have really ballooned in size. But even with all of those people sitting in front of a computer 8 hours a day, every day, forever, these organizations do not exactly have a reputation for high-velocity output. And part of that is just that like big tech has gotten really big, and it is fundamentally more difficult to iterate on a product that's used by millions or billions of people than it is to iterate on one that's used by hundreds or thousands of people. But having seen inside these organizations, I think that there's something more going on here. I don't think that explains everything. And I think, again, it is related to this intertwined relationship between vision and engineering. Anybody who is managing an engineering organization today will have some kind of management philosophy that is in some way downstream of, derivative of, in the zone of, somehow adjacent to or related to Agile. The general thesis being that hierarchical decision-making, where information flows upward in the form of reports and summaries and executive summaries, and the decisions flow back down in the form of budgets and headcount and priorities, is too slow. And so instead, organizations should be composed of autonomous teams, teams that act autonomously, and that the function of leadership in an organization like that is to create alignment across autonomous teams. Which sounds like an improvement, but it also sounds familiar. It sounds like this way of viewing software development and engineering, that you start with some vision, and then you communicate that vision to a collection of autonomous teams who will then do the engineering for that vision. And it doesn't leave as much room for this idea that vision and engineering are often intertwined and bidirectional, that engineering often needs to inform vision and vice versa. This is made worse by the fact that autonomous teams look a lot like, okay, thanks. Autonomous teams look a lot like black box abstraction layers. That they almost seem like a microservices architecture inside an organization. Okay. Sorry, I just need to be able to see the next slide on this monitor. Cool, thank you. Right. So yeah. So the autonomous teams oftentimes look like black box abstraction layers in themselves, almost like a microservices architecture. And when you have teams of people that are treated as black boxes, oftentimes I think it can be difficult for autonomous teams to have the insights that are actually necessary for excellent outcomes. Okay. So right. So. Correct. Okay. One thought experiment that I like to apply to organizations when I'm trying to assess the health of an engineering organization is to imagine that that organization is Skype at the dawn of mobile. I don't really know anything about Skype. I don't have any insight into Skype as an organization. I'm just an observer. But I think that they found themselves in an interesting situation. So imagine you're running Skype at the dawn of mobile, and you have all these engineers siloed into autonomous organizations, autonomous teams. And you, as the Skype leadership, have the insight to see that mobile is going to be really important. And so you create alignment by communicating that as a priority across the organization. Mobile, this is the thing everyone should be focused on. Even if everybody in the organization is now aligned in their autonomous teams that like mobile is the priority, we have this existential thing that we need to be thinking about, it's still a really big lift. The product is 100% organized around the desktop model. You have a user UX that is centered around the concept of being online or offline, concepts that just don't exist anymore in the mobile world. The communications protocol that your product uses is this like semi-distributed mesh that is dependent on having a background connection 100% of the time open to some remote server. That's not going to be possible on a mobile device. You have this concept of nodes and supernodes where you're routing traffic through other users. That's not going to be possible on a mobile device. So clearly, things need to change. In fact, everything needs to change. But the problem is that the change that every autonomous team needs to make is dependent on the change that every other autonomous team needs to make. That once again, we have this situation where the product is going to be this intertwined and bidirectional relationship between vision and engineering, where the way that the product looks is actually going to be informed by the engineering process and vice versa. But that if you have everybody in the organization composed of these black box abstraction layers, it's going to be very difficult for anybody to make that change. It's not going to happen. And in fact, I think the less people inside of an organization are comprised of black box abstraction layers, the more effective that organization is going to be. And even if you see this as like this black swan event that isn't going to happen that frequently, a complete paradigm change like the introduction of mobile devices, I think organizations that aren't capable of making this kind of change are leaving a lot on the table. The picture that I'm trying to paint here is that we spent the past 20 years onboarding people into software by putting them into black box abstraction layers, and then putting them into organizations composed of black box abstraction layers. My pitch to you is that this thing that I'm talking about, where understanding is at the basis for most of the important developments and the history of discovery in software, this thing where understanding yields these truly excellent outcomes, is also the fundamental inescapable foundation of all security research. That security is almost the inverse of what I've been talking about. That security is the process of looking through abstractions in order to actually understand how things work, what's beneath them, and sometimes understand them better than the people who built them to begin with. And that when you do that, you can look for the ways that these interfaces do not stack cleanly on top of each other, look for the ways that these things are leaky, look for the ways where, in combination with other things, they can yield unexpected outcomes that are oftentimes exploitable. And that's cool and valuable within the context of security. But what I'm trying to say is that without knowing it, I think you, the people in this room, have actually inherited the earth. That we have spent the last 20 years undermining our ability to create good engineers by onboarding them into these black box abstractions, putting them on teams composed of black box abstractions, and that while the rest of the world has slowly been organizing themselves to understand less and less about how software works, that you, the people in this room, have been doing the opposite. What I'm trying to say is that you all are the ones who have been sitting in the library, learning the spells, actually understanding how all of this works. And that, like the Harry Potter world, the only thing that you need to use to make use of this knowledge is a computer. And it doesn't even have to be a good one. All you have to do is look at the things that you understand really deeply, look at the problems in the world around you that you're acutely aware of, and then think about the ways that the things you understand really deeply can be applied to the problems that you're acutely aware of. I started Signal alone with a laptop, sitting on the floor of a hallway outside of a security conference. I hope that this week, some of you do the same to create something even better. The only secret is to really begin. Thank you.
Well done.
Thank you.
Hey, so we still got, look at that, 15 minutes. So I've got all these questions.
Shoot.
Okay. Hey, first, maybe just get us back, go back in time. Like, you were doing a lot of, well, first off, you're one of the few cryptographers I actually know that's like approachable. You use words I can comprehend. And you were doing a lot, I think, security kind of related projects, and you settled on Red Phone. Maybe just like talk about the origin story a little bit, and when did you know that that was the one you were going to put your energy into and not something else? Like that, that sense of, success.
Right. Right. Well, I think the history of privacy-enhancing technology takes some twists and turns. And early on, there were people who thought that privacy, cryptography were going to be important and necessary tools for the internet. And there were some early experiments with those ideas. And then the web happened. And the web was kind of bad for cryptography in a lot of ways because to have end-to-end encryption, you need to have ends, which means you need software endpoints that can maintain some state. And if if all software is now a web app, a web browser is fundamentally just a view onto a server where the data lives, and you don't store any state in the web browser, and the logic itself doesn't exist in the browser. And so it's hard to have end-to-end encryption, for instance, like with something like webmail in a browser. And so the introduction of mobile devices where you could run software on phones, and that software wasn't just a web app, it was actually real software that ran on the phone that could maintain some state, was a big opportunity. And so when I started working on Red Phone and TechSecure, it was because I saw that we finally had the opportunity to build something that was end-to-end encrypted.
The technology caught up.
Right, yeah, it's like Mark says, we can create our own history, but only under the circumstances that are communicated directly from the past.
Right. So then you build it, and now it's becoming successful, and it's growing. And then when do you get that realization that you've built something maybe bigger than yourself, or you have to involve more people for your vision to be achieved, but then now it's also their vision and not 100% your vision, you know, that sort of...
Yeah, I mean, I think one thing about software today is, in many ways, I think software development has gotten more difficult over time. And this opportunity that I'm talking about also increased the cost of developing software, because it used to be that you only had to write one version of your software, and now you have to write 3 versions. You need like at least 2 mobile apps and a desktop app. And so that is not a really sustainable thing for one person.
So then it turns into teams.
Yeah.
And so, so then this is occurring while you're gaining success with Signal, and now you have to build out because you have more and more users, right? So you're scaling out, and so I think we were talking a bit, and I'm going to misquote you, but you were saying something. There's essentially like 2 kinds of software development: at scale and not at scale.
Right. Well, I think software is fundamentally expensive to build. that when you think about, I admire, or I envy, writers, filmmakers, musicians, people who can create something and be done. So it's like you can record an album, and then that's it. You got your album, and there's no real work that you have to do to maintain the album. Like, it just exists, and people can listen to it, and for 20 years, people continue listening to it. You didn't have to do anything. Software does not work like that. Software is never finished. You cannot make software and be done. So what software requires is at least a person and maybe a group of people sitting in front of a computer 8 hours a day, every day, forever, for that software to continue to exist. And so that makes software somewhat expensive. It's not something you can just do one time and be finished with. You have this ongoing cost that never stops. And so that is kind of an expensive proposition, but the benefit of software is that it can exist at scale really easily. And I think the problem is that today, what it takes to develop software means that it does have to be at a certain scale in order to support the costs associated with building it. And so I think it's difficult for projects that exist at really low scale for like 100 people. If you have 100 people using some software, and no matter what the business model is, if they're willing to pay $10 a year or even $10 a month, it's difficult to support that piece of software. And so you kind of have to be at scale.
And so, so then the kind of businesses you have to engage in are things that have to happen at scale, right? A lot of small, boutiques, one-offs, you just kind of lose out on that.
Yeah, I think it's difficult to, it's difficult to put the time and energy that a piece of software requires in if it exists at a really small scale, which is, I think, an unfortunate thing about software. And in a lot of ways, I think if we want to live in a world where we can have software exist at smaller scales, or where software maybe serves our interests better, then we need to make software development cheaper. And that's actually one thing that I'm optimistic about AI for.
So I think it was Roger Dingledine from the Tor project. I was talking to him once, and I asked him, what can I do as an individual or a system owner, running some servers? What can I do to be nefarious, a good kind of nefarious? And in the old days, in the cypherpunk era, I could contribute. I could run a PGP key server. I could run a remailer, a mixmaster remailer for email security or whatever. And you fast forward a bunch of years, nobody cares about that stuff anymore. It never really had a big impact. And Roger said, yeah, everything's done in teams now, right? If you want to have an impact in the world, privacy, security, whatever, you need a lot of people. And that kind of goes along with your idea of engineering. It's a team effort. But when you started Redphone, that wasn't the case, because you, as an individual, or TechSecure, you made this huge contribution, right? And so it happened along your journey.
Yeah, I don't think that you need really large groups of people to build most software. I think most engineering organizations today are kind of overstaffed, and there's perverse incentives that have resulted in these large, inefficient teams. I think you can do a lot with a small group of people, and even as an individual. I think that what you're talking about is also, there's been this transition over time where the scale has just changed things. That I think in the beginning, when we were imagining privacy-enhancing technology, in a lot of ways we didn't take our ideas seriously enough, and did not fully imagine what it would mean for those ideas to exist at large scale. I think one problem with early interest and efforts in privacy-enhancing technology was it was this era when computers were for computer people. There was normal people, and then there were computer people. And computer people were the people who used computers, and normal people sort of didn't really. And when early computer visionaries in the privacy space imagined the future and thought about how important computers are going to be to everybody, they imagined that what we were going to do is develop really powerful tools for ourselves and then teach everybody to be like us. And that is not going to work. And it's kind of laughable in retrospect, but I think that's how that's how we imagine the future being. And so we sort of just imagine that it's like, yeah, like individuals would start running, we would teach people how to run a PGP key server, and then we would teach everybody how to verify.
Create a web of trust, and then we'll all
we'll just hang out over dinner and sign keys for each other or whatever. And I think there were a couple problems with that. One is that we were just wrong. And then I think the next thing that happened is that the people who understood how to do those things actually started to develop an identity around it. One thing that I think about sometimes is like Napster. Like, why did file sharing take so long? Right? It's like one way to think about it is like, okay, well, there was Where's forever. There's like these Where's groups, and that's a form of file sharing. And then there was MP3s for a while. It took a while for Napster to happen. And I think part of the thing was that the people who understood the power of file sharing had developed an identity around knowing all of the kind of intricate, arcane ways to get into the right places, to get the stuff, to use the tools that were kind of hard to use, and didn't actually have much of an interest in making that broadly available because it would undermine their identity. And it took some other kids to come along and be like, I'm going to make something for everybody, before it became super obvious. And I think the same thing kind of happened in the privacy space, where people who really understood the intricacies of all the PGP command line options and how to install OTR and all this stuff had developed a kind of identity around the arcane knowledge of those things, and a set of cultural norms that they were, myself included, kind of hesitant to undermine, because it would mean undermining our own identities.
So you have the success, you're growing, now you're at scale, and now all of a sudden you have to start making informed decisions on privacy trade-offs. And one of the most fascinating things I think in watching Signal evolve is that there's a lot of people willing to tell you what the privacy trade-offs are and speculate about what decisions should be made and why, but they're not in the driver's seat, and they're not making decisions for millions and millions of people. And you are. And so I figured there was a handful of people in the world that actually understood how to make an informed trade-off while you're trying to achieve the best outcome for the most number of people. Can you maybe just talk about that a little bit?
Yeah, I mean, I think the thesis is probably don't make trade-offs, but I think what's actually difficult is to develop an intuition for developing a product that many people will use in general. And part of the problem was that I was coming from this world of the arcane tools, right? That I had done some brain damage to myself in terms of having an intuition for what people's expectations are from software. So when I first started working on Signal, I had a phone with a hardware switch soldered into it so I could turn off the microphone with the switch. I ran my own mail server, and I had it PGP encrypting mail as it arrived, so that all the mail in my mail spool remotely would be encrypted. And then I was running some thick mail client locally that would IMAP that down and PGP decrypt it locally. But I had cross-compiled that into some weird architecture and was running the software in QEMU or something like that, so that if there was some memory corruption vulnerability, you'd have to guess which architecture it was, and you would not be exploitable, which is insane. I was doing a bunch of insane things. And I think the problem is that a lot of people in that world who are super familiar with this stuff live an equally, at least at the time, were living an equally insane life, and so had different expectations for what is a reasonable product to develop. But the goal, I think, the goal of all software development is to manage complexity. That when you're working on a large project, the thing that you're really trying to do is manage complexity. And I think that applies to a product as well, that you're trying to manage the complexity of the product through the user experience. And I think for people coming from the privacy space at the time, the intuition was to take the complexity and push it onto the user. So it's you have some complex decision that needs to be made. Just make the user make that decision.
Right. Do I trust this fingerprint?
Right, exactly. Push the complexity onto the user. And I think the goal, just as the goal in software development is to manage the complexity of a software project, the goal of product development is to manage the complexity of those kind of questions so that you take on that complexity instead of making the user deal with it.
So, final question. No, maybe I don't have a final question. I think you already answered that. I was going to ask, why did PGP never catch on? Why did SMIME never catch on? Why are these large privacy-enhancing technologies that had a lot of promise, we're not getting the benefit of them? We're getting the benefit of Microsoft running a really secure virtual machine, right? Or Postfix running a really secure mail server. And it's because the software engineering has gotten better or more secure, not because a new security-enhancing technology came along, right? I think maybe you mentioned it's also because when you're running something like you're terminating your TLS in Amazon, now they have to worry about.
Right, yeah. I think for those reasons are why those things never caught on. But I think in many ways, the goal of a privacy project is to make the way that software looks the same as the way that it works. So if you have a messaging app, the way that it looks is you type a message and you send it to somebody and they receive the message. And the problem is that in the past, that's not actually how it worked. That many people had access to that message. That if the user experience or the UI had been honest to the representation, every message with your friend would have been a group chat with your friend, Mark Zuckerberg, everybody that works at Facebook, all the advertisers that would have been the honest user interface. And so the privacy projects are just about making those two things the same, making them consistent, where if you send something that only one person it shows receives, that's actually what's happening on the technological level. And I think the other projects you're mentioning were not as focused on just trying to create that consistency. And I think that's actually the ongoing opportunity in privacy technology. Look for the ways in which the user interface does not match the reality of how these things work, and then try to bring them together.
Fantastic. All right, let's give Moxie a round of applause. Thank you very much. Okay, everything kicks off at 10:20. You've got about 25 minutes to get to the sessions. Thank you very much.